We're coming up on the third anniversary of the start of the COVID-19 pandemic next month. And though the virus is still with us, the mRNA vaccines have protected so many people from serious illness and death. As you probably recall, they were the first mRNA vaccines ever approved for national rollout. Before mRNA, most vaccines consisted of part of an inactivated virus, or part of a live but weakened one. Those vaccines show the immune system a sign of the enemy it needs to be ready for. The mRNA vaccines work differently, though. They don't contain the virus itself, but the genetic information of a special protein that the virus makes. It's a protein that the body knows is foreign, and that helps the immune system recognize the arrival of the virus itself. Because mRNA vaccines don't rely on manufacturing actual viruses, they're much easier and cheaper to produce at scale. Incredibly, the mRNA COVID-19 vaccines were developed, tested, and put into people's arms in less than a year. But if they were so new, how did this all happen so fast?
The people who really took those COVID vaccines to the clinic actually were cancer vaccine people and had been using that mRNA technology for quite a few years.
Nora Desis is director of the Cancer Vaccine Institute at the University of Washington School of Medicine and the founding editor of JAMA Oncology.
One of the reasons why mRNA was able to advance so rapidly is that its safety profile in many, many, many cancer patients had already been defined. The really laborious work of trying to develop a cancer vaccine was able to result in immediately cassetting the COVID antigen into existing vaccines and being able to rapidly take them to clinic.
In fact, late last year, Moderna and Merck reported on the trial of an mRNA vaccine targeting cancer, in this case, melanoma. It's early, but the results look promising. So, what's next? From the Freakonomics Radio Network, this is Freakonomics MD. I'm Bapu Jena. Today on the show, how are scientists targeting the immune system not just to save us from the latest virus, but to bolster our fight against cancer?
The immune system can actually create the type of immune response that has the capability of destroying cancer.
And are the positive results of that recent mRNA melanoma vaccine a sign of things to come?
I can tell you it's been a roller coaster ride.
Where are you from originally?
Chicago, Illinois.
I was born in Chicago in a hospital called Michael Reese Hospital, which I'm not sure if it's still around.
I was a resident at University of Illinois and walked the corridors of Michael Reese.
Ah, okay. Nora Desis is a big deal in cancer vaccine research. She may even be on the cusp of delivering a successful vaccine to treat breast cancer. But I think it's good to start with the basics here. So, what exactly is cancer?
Cancer, to me, are cells in tissue that used to be normal that through a series of genetic alterations have now gained the potential to grow wildly on their own with none of the stop gaps that our body has in place to stop them.
And cancer can arise from a number of different places. What's the sort of mechanism?
Some of the mechanisms can depend on specific type of cancers. So for instance, viruses, cancers like cervical cancer or liver cancer can be caused by viruses. Environmental aspects, smoking, can cause cancers such as lung cancer, bladder cancer. But there are still very common cancers, such as breast cancer, where the majority of patients don't really have any of the known risk factors. One of the things we do know is that cancer really is a disease of older people. children rarely get cancer. And so the idea that a host of genetic alterations kind of accumulate without your body being able to fix them over time as we get older is also a theory of why you develop enough genetic mutations to result in cancer.
So something happens that prevents the body from being able to say, okay, this is not right. What is the role of the immune system in that process?
The big question driving the field 30 years ago was, does the immune system even have the capability to see cancer and respond to it? And we know that it does. We know in some people, in some cancers, the immune system can actually create the type of immune response that has the capability of destroying cancer.
The immune system is triggered by something called antigens. They're basically markers on the outside of a cell or a virus that indicate to the body that something is foreign. With cancer, these tumor antigens, as they're called, can reflect proteins that are unique to cancer cells, or proteins that are produced in normal cells, but at much lower quantities. Sometimes these tumor antigens are hidden in cell membranes, but in cancer, they become uncovered and visible to the immune system. And when there are lots of mutations driving a cancer, the immune system might be more likely to recognize the tumor as foreign. In all of these cases, there's something about the cancer cells that the immune system should be able to recognize and act upon, but it doesn't. So, why not?
The vast majority of cancers are not highly mutated, at least solid tumors like colon cancer, prostate cancer. There are proteins expressed in and on those tumors that can stimulate the immune system. But the proteins are still too close to ourself. So the immune system recognizes something is wrong, but it will not make that rip-roaring, tissue-destructive immune response directed against the protein. We now know that almost all cancer patients do have an immune response directed against their cancer, but only a minority of patients have been able to stimulate the right type of immune response that has the potential to kill the cancer.
What do you mean by the right type of immune response?
The right type of immune response would be a T cell response.
T cells are a powerful kind of white blood cell. The other, more basic immune response comes in the form of antibodies produced by B cells, which are different.
We know cancer patients have a lot of antibody response directed against their cancer, but the antibodies don't bind very strongly to the tumor, and they don't really affect a tissue-destructive immune response. But if you have type 1 T cells in your tumor, you fall into the category of having that potential, if you can expand those T cells to high numbers, to have your immune system assist in eradicating cancer.
The number of mutations in a specific cancer is an important factor in just how effectively we can harness the immune system. On the one hand, more mutations suggest that all the stopgaps to slow cancer growth are basically gone. Historically, highly mutated cancers have been a bad prognostic sign for patients. But on the other hand,
the more mutations your body can recognize, the better. If you only have 10 mutations in your tumor, the likelihood of those mutations being able to stimulate T cells is low. If you have tens of thousands of mutations, the likelihood is much, much better. So we look for tumors that are highly mutated, such as melanoma, some types of lung cancer. You may have 40% of the people being able to have that type of immune response.
Talk to me about the landscape of different immunologic-based treatments. Can you walk me through the problems that they're trying to solve?
Even though patients can develop those good types of immune responses, they very rarely make their own tumors go away with no help. And that's because the tumor itself has all types of mechanisms to kind of check that immune response and prevent it from really getting a hold and being able to eradicate the tumor. And we call many of those mechanisms immune checkpoints. The very first drugs targeting these were called immune checkpoint inhibitors. And when these were infused into patients, the T cells were able to attack the tumor, and actually in patients with very advanced stage tumors have significant anti-tumor responses, especially in those patients with highly mutated tumors. And in a minority, 5% of patients or less, could actually result in complete eradication of the tumors.
Wow. Can you give me an example? What type of cancer? Are you talking about melanoma? Or are there other cancers where this would be true?
We've seen it in melanoma, where we have patients who've had a complete response, and they've been very long-term survivors. We've seen it in lung cancer, and we've seen really dramatic responses in many other types of cancers, very highly mutated colorectal cancers, for example. But these types of complete responses are quite rare.
Coming up, could new therapies make these complete responses more common or even help people avoid getting cancer at all?
There's a new field in the last decade looking at vaccines for primary prevention of cancer.
That's after the break. I'm Bapu Jena, and this is Freakonomics MD. Before the break, Nora Desis explained the importance of immune checkpoint inhibitors as a recent therapy for some cancers. Even though cancers have features that should make them appear foreign to the body's immune system, they have mechanisms that cloak them in a sense. They hide using checkpoints that prevent the immune system from recognizing cancer cells as foreign. Immune checkpoint inhibitors are drugs that work by overriding those checkpoints, allowing the immune system to see the cancer cells for what they are, foreign. But the options don't stop there.
There are therapies such as CAR T cells. CAR T cells is an approach where you can take a killer T cell, take it out of the body, engineer it to be a super killer, and grow up a whole bunch of them and infuse them into the patient. So it's almost like replacing the patient's entire immune system with an immune system that's nothing but those killer T cells.
CAR, or CAR, stands for chimeric antigen receptor. It's a receptor that's specifically designed in a lab and then added to T cells collected from a patient. Those CAR T cells are genetically engineered to recognize and kill cancer cells. This approach works especially well with blood cancers.
One of the things that we know with blood malignancies, which is very different from solid tumors, is that the cells in the malignancy may be very similar to each other. And so you can create a CAR T cell that's directed against that protein, and that CAR T cell will attack every single blood cancer cell that was present in the patient. The issue with the CAR T cells is we need to figure out a way to make them last longer. They generally do their killing and then they themselves die. But the more technology that's going into these CAR T cells to figure out how to make them live longer may be a way to permanently cure people with blood malignancies.
Why don't those T cells develop natively? What is it about the native process that breaks down?
One of the things we know about blood malignancies like leukemias is they're extremely rapidly growing cancers. Literally, you can be well 1 month and the next month have an overwhelming leukemia. Whereas in the body, you might have only a small number of your T cells being a super killer at any one time. If you're someone with leukemia, you need to have 100,000 of those cells in your body right now. And with technology, we're able to deliver that.
Tell me about mRNA technology. How is it being used here?
mRNA technology is really being used most in terms of the development of cancer vaccines. If you're developing personalized cancer vaccines that are directed against mutations in a patient's tumor, and you have to make a lot of mutations, you can do that pretty rapidly with an mRNA vaccine. The second thing is the vaccines are very effective at generating type 1 T cells.
Remember, type 1 T cells can help your immune system eradicate cancer cells, but only if you have a lot of them. It's a balancing act. With fast-growing cancers, there need to be enough T cells that are circulating in the body to recognize the cancer cells as foreign. The body typically can't do this on its own, which is where immunotherapies come in. mRNA vaccines in particular are one way to stimulate this immune response from T cells.
So if you have DNA or mRNA encoding an antigen, the antigen in that vaccine is created by your body in the cell and presented naturally to your immune system. Whereas other forms of vaccination have a tendency to generate more of an antibody response.
In an mRNA cancer vaccine example, is it personalized for the particular tumor antigens that a person has, or is it more sort of cancer disease specific? So there's certain antigens that we see on certain cancers, and we design an mRNA or DNA vaccine that encodes those particular antigens. What determines how that genetic material is developed?
There are two distinct approaches to cancer vaccines. One is an approach where if you have a highly mutated tumor, you can identify the scores of mutations and you can rapidly generate a vaccine specific to that patient and then immunize the patient to cause those important T cells to expand further. And people have shown that giving that along with an immune checkpoint inhibitor can be very effective in terms of getting that type of immune response that can eradicate cancer. On the other hand, most patients with solid tumors don't have highly mutated tumors. But we know that there's a breast cancer subtype defined by the fact that they have a protein called the HER2/neu protein. It is about 30% of all breast cancers. And patients have immune responses against that protein. You can create a vaccine and immunize patients to create that type 1 T cell response against HER2. And those types of vaccines are more universal. They are not specific to the patient. They're specific to the type of cancer.
And those types of vaccines would be used in the classical sense as vaccines to prevent cancer from developing, or would they be used as therapies to either prevent recurrence or to actually treat the underlying cancer?
The vast majority of vaccines being developed today are therapeutic vaccines. And I think one of the things we've learned about applying vaccines clinically is they work better when tumors are held at bay. So we're beginning to see many clinical trials being run in the setting of preventing cancer relapse. So taking patients who've been totally treated for their cancer, but they are at very high risk of relapse, and then immunizing them with a cancer vaccine, either a personalized vaccine or one of these vaccines that's really targeting a tumor type. However, there's a new field in the last decade looking at vaccines for primary prevention of cancer, immunizing patients who either they have a genetic high risk, and so you're trying to immunize them against the cancers that would potentially develop, or they have a pre-cancer lesion, such as an adenoma in the colon or ductal carcinoma in situ, which is kind of a pre-cancer for the breast. And you're developing a vaccine that would treat those lesions that may be associated with the eventual development of cancer.
Colon cancer seems like it might fit into this bucket because there are these hereditary forms of colon cancer. Is that a good example, or are there others?
Well, there are many others. There are syndromes, such as Lynch syndrome, where patients have a genetically high risk of developing different types of cancers. We also know that there are patients who have familial pancreatic cancer syndromes, where those patients can be immunized prior to the development of pancreatic cancer. There are clinical trials that are ongoing now, just starting to look at cancer prevention vaccines against these types of cancer-associated proteins and mutations.
If you were to forecast, let's say, 10 to 20 years from now, how different do you think the cancer treatment landscape will be than it is today?
I can tell you it's been a roller coaster ride the last 2 decades. So I feel pretty confident saying it's going to be completely different from where we are now, because today is completely different from where we were 10 years ago. Literally every day, things are being published where I'm like, wow, I really need to know this. This is life-altering. That's how fast science is advancing in terms of understanding cancer etiology, the most important pathways, and how to treat them.
I wanted to chat with Nora because the work that she and others are doing to figure out how the immune system can be used to fight cancer is so important. It's changing lives. I know we talked about a lot of technical stuff, but maybe I'll end today's episode with an analogy. For most of us, when we get sick with a bacterial infection, our immune system recognizes the bacteria as foreign. Our body mounts an immune response, but usually that's not enough. Bacterial infections work quickly, and we often need antibiotics to assist the immune system. To understand why we need both of these things, think of people who you know who are immunocompromised. Even with antibiotics, they have a hard time battling infections because they're missing an important part of the response, the immune system. Now, think about cancer. When it comes to cancer, nearly all of us are practically immunocompromised. Our immune systems don't adequately recognize the cancers in our bodies as foreign. That's why, up until recently, we've had to rely on treatments like chemotherapy or targeted cancer medications to fight the cancer alone, without the help of our immune system. What Nora told us about today are all the ways scientists are trying to get our immune system back in the game, to help it be effective in fighting cancer in the same way that it's effective in helping us battle infections. On that note, I'd like to thank Dr. Nora Desis for taking the time to talk with me today. And thanks to you, of course, for listening. And that's it for today's show. Let me know what you thought about it. Have you or a loved one been treated with immunotherapy? Would you take a preventive mRNA cancer vaccine? I'm at Bapu at Freakonomics.com. That's BAPU at Freakonomics.com. Or leave us a review wherever you get your podcasts. Coming up next week on the show, recent breakthroughs in biotechnology have transformed what's possible when it comes to diagnosing and treating rare genetic diseases.
It really feels like we're entering the golden era of computational diagnostics. This isn't some hypothetical something that will exist in 2033. This exists in January 2023.
But financial and regulatory roadblocks mean that many people who might actually benefit from these breakthroughs are still waiting.
Our ability to engineer these CRISPR medicines has far outpaced how these medicines are actually built, tested, and put into human beings.
Why aren't these medical advances reaching their full potential? And who stands to benefit if we can overcome those roadblocks? That's next time on Freakonomics MD.
Freakonomics MD is part of the Freakonomics Radio Network, which also includes Freakonomics Radio, No Stupid Questions, and People I Mostly Admire. All our shows are produced by Stitcher and Renbud Radio. You can find us on Twitter at Dr. Bapu Pod. This episode was produced by Sarah Lilly and mixed by Eleanor Osborne. Julie Canfer is our senior producer, and Lyric Bowditch is our production associate. Our executive team is Neil Carruth, Gabriel Roth, and Stephen Dubner. Original music composed by Luis Guerra. If you like this show or any other show in the Freakonomics Radio Network, please recommend it to your family and friends. That's the best way to support the podcasts you love. As always, thanks for listening.
Is there a way to induce more tumor mutational burden?
There are actually people looking at that, but highly mutated tumors have a tendency to be much more aggressive.
That's why you don't want economists designing therapeutics, in case you're wondering.
The Freakonomics Radio Network, the hidden side of everything.
Stitcher.